Hi there. This PowerPoint video lesson is on the graphical transformations of functions. Okay, so first off, we're going to look at 8 different kinds of transformations. I would like to think about them as 4 pairs. So 1 with 2, 3 with 4, 5 and 6, and the last pair 7 and 8. Also, I would like us to think about them in 2 groups. So first off, the transformations that operate on the outside of a function. Here we can think about the transformation as changing the y values. If the transformation operates on the inside of a function, then it's the x values that change. So in our 8 transformations, number 1 is a shift up by c units. Transformation number 2, where we have f of x plus c inside the function, that's going to be a shift to the left by c units. Transformation number 3, where we have a multiple k outside of the function f of x, is going to be a stretch by a factor of k in the y direction. Transformation number 4 is a compression by a factor of k in the x direction. Number 5, minus of f of x, is going to reflect the graph across the x-axis. Number 6, f of minus x inside the function, is going to reflect the graph across the y-axis. Transformation number 7, the modulus of the whole of the function f of x, reflects only the negative y values across the x-axis. And the final transformation, y equals the f of the mod of x, or the modulus of x inside the function. We're going to actually ignore the part of the graph where the original x values were negative, because mod of x can never take a negative value, and we then reflect the positive x values across the y-axis. Okay, it's going to be a lot better with actual examples. So first example of transformation number 1, where we have f of x plus c. So adding a constant outside a function is going to shift the graph up by 2 units in this case, with f of x plus 2. Okay, so plus 2 outside the function. Translation vector of 0, 2. No change in the x direction, shifting up by 2 in the y direction. Second example of the same transformation, if we have a straight line graph with a gradient of 2, so f of x is 2x. If we apply transformation of f of x minus 4 outside the function, shifts it down by 4 units. So translation vector of 0, minus 4. No change in the x direction, 4 units down in the y direction. Second transformation, where we have f of x plus c inside the function. Okay, so the graph we're going to start off with here is a very specific cubic function. So we have roots at 2, 0 and 0, 0. Also, we can notice that it has the quadratic kind of shape and bounces at the root 2, 0, associated with a part of the function that's x minus 2 all squared. There's also the graph passing through the root at 0, 0. So when we apply a transformation f of x plus 2 inside the function, and if we call this new graph g of x, it's going to actually shift the graph 2 units to the left. Okay, so we need to be careful, and if we apply the transformation and substitute into the original function, so everywhere where we had x before, we're going to replace it with x plus 2. And if we rearrange, we find that the function goes to x squared multiplied by x plus 2. And when we look at that function, we can see that the roots are going to be at 0, 0 and minus 2, 0. So when x is 0, g of x is going to be 0, and g of x is also going to be 0 when x is minus 2. So now when we put these two graphs together, it makes a lot of sense because we can see exactly where the roots are. The cubic functions are the same shape, and everything has been shifted 2 units to the left. Okay, so although it's x plus c inside the function, we need to remember we're actually shifting by c units to the left. Okay? Don't be tempted to make the mistake and fall for the trap of wanting to shift it in the positive x direction. Okay, we're not shifting to the right. Third transformation, we have the basic quadratic function here again, starting with f of x as x squared. If it's a transformation of 2 times f of x, it's going to be a stretch in the y direction with a scale factor of 2. Okay, and we have our table of values here showing the function, the values for x squared corresponding to x values of consecutive integers from -4 up to 4. Okay, so what we notice is that when f of x is 0, 2 times f of x does not change the value at all, it stays as 0. If we start with 1, these values are doubled, so they're stretched by a factor of 2 up to the point 2. The coordinates at 2, 4 and -2, 4 stretch up to 2, 8 and -2, 8. The same happens with the other values. They're all stretched up by a factor of 2. Okay, and this is going to be applied consistently across the whole graph, the whole function. The values don't have to be restricted to the whole numbers. Our fourth example, transformation number 4, where we have f of kx. So the transformation is inside the function. It's the x values that are going to change this time, and the x values are being compressed by a scale factor of 2. Okay, so it's a compression by scale factor of 2 in the x direction. Again, with our table of values, the values associated with the points coordinates 416 and -416, they're compressed by a factor of 2 to 216 and -216. And another pair of values, we can see that the points at 2, 4 and -2, 4, they're going to be compressed to 1, 4 and -1, 4. Okay, so we can also look at the function. I've called this one h of x, and if it's transformed with f of 2x, the 2x inside the function, then everywhere where we had x before in the original function f of x, each x that appears in the original function is now going to be replaced by 2x. So we're going to actually have 2x all squared, which is actually 4x squared. So for comparison, we had 2 times f of x versus f of 2x, and we can see the difference between the two. Okay, now I've shown us also algebraically that the first transformation in this pair, transformation number 3, the stretch by a factor of 2 in the y direction, that's 2x squared. If it's 2x inside brackets, we actually have 4x squared. Okay, so 2x all squared, which is 4x squared. That's actually a compression by a factor of 2 in the x direction. I'm also going to look at this example, revisiting transformation number 3. Okay, so we said we were going to stretch in the y direction by a factor of k. Here, it's actually the y direction stretch by a scale factor of a half. So what we need to be careful of is that actually, if we look at what's going on, if we look at the coordinates here, the y value is going from 10 to 5. So the coordinate is actually going from 110 to 15. The y-intercept is going from 02 to 01. Both of these points have the y value or the f of x value being halved. 10 halves to 5 and 2 halves to 1. Next point that also gets stretched by a factor of a half is the coordinate -1, 1. It goes to -1/2 with a negative y value this time. The coordinate at -3, -7 gets compressed to -3 minus 3.5, which is half of -7. But I wanted to focus also on this root. Okay, so the only invariant point, so the only point that doesn't change or vary after this transformation, is actually going to be the point where the y value is 0. Okay, so slight extension. How about if you test yourself? Have a go at sketching. We start with this function in red, this f of x. The cubic graph that's shown here, that's actually just the cubic graph, the x cubed graph, shifted up by 1 and to the left by 1. So you can see the turning point, the point of inflection, is going from the origin for y equals x cubed to the point -1, 1 here. Have a go to see if you're able to sketch what f of x over 2 inside the function is going to be. Our fifth transformation, the first of 2 reflections. This is a reflection in the x-axis and also a little bit of algebra. We can see the original function. The original function is a quartic. The coefficient to the quartic is positive, so it's going to be a w. This quartic actually happens to be symmetrical through the vertical line x equals 1. Quartics aren't symmetrical about the central vertical line in general, but we can see that actually when we apply the negative of f of x, it's just going to flip it across the x-axis to a quartic with the same roots at 0, 0, and 2, 0, but instead it's going to have an M kind of shape because the coefficient to the x to the power 4 term is negative. Sixth transformation, where we have a reflection in the y-axis, and if we look at some of the algebra, actually we can rewrite this original function where the roots are at 0, 0, and 2, 0. If we rewrite the function and substitute each time that x comes up in the original function with the negative of x, then we have the negative of x minus 2 all squared multiplied by negative x all squared. So if we recall that if we have a times x in brackets all to the power of n, this is the same as a to the power of n multiplied by x to the power of n. So negative of x all squared is actually the same as -1 squared multiplied by x squared, which is just x squared. And if we applied the same thing to the part that's actually negative x minus 2, we can factorize out -1, giving us the negative of, in brackets, x plus 2. And if we squared all of that out, we have again -1 all squared multiplied by, in brackets, x plus 2 all squared. So actually we've shown that after this transformation, f of minus x with minus x inside the function, actually this function is the same as x plus 2 in brackets all squared multiplied by x squared. So here, both of these functions, before and after the transformation, they have a shape of w, a quartic with a positive x to the power 4 coefficient, and we can see it gets reflected across the y-axis after the transformation to function with roots at 0, 0, associated with the x squared part, and another root at -2, 0, associated with the x plus 2 in brackets all squared, because when x is -2, y or g of x is also going to be equal to 0. our seventh transformation, where we have f of x, and if we take the modulus of the whole of it, any negative y values that we have are reflected across the x-axis. Okay, so here, back to the original function in red, f of x, let's look at the values where f of x or the y values are negative. So all values are non-negative for x values that are either less than or equal to 2. Once the x value goes above 2, y or f of x is going to start to become negative. These negative y values are reflected across the x-axis because we take the modulus of the whole of f of x. So it's the final y values that can never be negative after this transformation. Transformation number 8 is where we have the mod of x, or the modulus of x, inside the function. And again, we show what this function is going to look like. So again, we're starting with the line that's with gradient minus a half and a y-intercept of 0, 1. So now it's going to be the negative a half of the mod of x plus 1. So because the mod of x can never take a negative value, we're going to ignore the part of the graph where the x values are negative on the original graph. Okay, so we're going to ignore all of these negative values. We're then going to reflect the positive x values across the y-axis, because where x was 1 before, this is going to take the same y value now as where x was minus 1. So when x is minus 1, when we take the modulus of minus 1, it's going to give us the same value for g of x, or the f of mod of x, as when x is 1. And after the transformation, when x is minus 2, it's going to actually be the same for f of mod of x as when x was 2 before. Okay, so all of the f of x values for x values that were positive, these are actually being reflected across the y-axis. And that's all the transformations we're going to look at in this video. I hope that was of some help, and feel free to pick the slides or part of this video that is of help. Thank you.